Hi everyone, my name is Neha Kardam and this is the fifth lecture on electronics communication. In this lecture, we will learn about AM reception. So let's get started. Here on the screen, you see a radio receiver's block diagram. In the previous lectures, we have covered the block diagram of radio receivers. So we can make a guess like what all these blocks consist of. As you know that radio receivers completes a communication system, and without a receiver, a transmitter is useless. Receivers comes in many different forms. They can be designed to receive voice, digital data, and many other kinds of signals. So let's see what are these blocks consist of. This must be the antenna. So here, this is antenna, and this is the bandpass filter. And the next comes the RF amplifier. And after that, we have a demodulator. And then we have audio amplifier. And then lastly, we'll have a speaker. And you know that at a receiver side, when you receive the signal from here, you know that antenna, the main function of antenna is to convert the electromagnetic energy into the electrical signals, and that signal will go to the bandpass filter, and this filter will select the frequency, and then once the frequency is selected, then it is passed through the radio frequency amplifier and then further to the demodulator. And here at the demodulator, you know that the function of this demodulator is to separate the carrier frequency from the information signal, and that information signal which is our main message we want to receive will basically pass through here and will go to the audio amplifier and further to the speaker, and here at the speaker side we receive the information signal. So the next what we are going to see is the demodulator or the AM detector in the next slide. So here you see this one of the circuit of the AM detector, and there are many circuits available for the detector, and the most common you see here is the diode detector type. And here diode is used, and you know it is a non-linear device. It can modulate and demodulate AM signal. Here the diode you see is a germanium type diode, and this is used the use of this type of diode is common in AM detectors. A silicon diode usually requires around 0.7 volts of forward bias to conduct, and whereas germanium diode requires around 0.3 volts. This germanium diode here increases the sensitivity of a receiver greatly. Now here in this circuit, you see the AM input is coming in here. So if you test at a point, your signal will consist of the carrier frequency as well as the information signal. So you see here on the right hand side, this represents your original information signal, and here at the test input A here, this will consist of a carrier frequency. You see this is a carrier frequency, and if you remember on the envelope we have our information signal going in, which is superimposed on this carrier frequency signal. So this signal is attached to this carrier frequency signal, and that's what we see here at a test station A. After passing through the diode, this diode will behave as a rectifier, and you know that during the positive half cycle it will pass the signal, and during the negative half cycle what will happen, this is the positive and this is the negative, so this will become the reverse bias, so it will not pass anything in the reverse cycle or the negative half cycle. So in the positive half cycle, you see we have this, so this signal is being passed over here, and that's what we see at a test point B here. And this signal consists of a modulated AM carrier signal, sidebands, the information frequency, and a DC level. Now, what we desire is to recover the information frequency and discard the AM carrier signal, AM carrier signal, so that the main message can be received over here. So this job can be performed by a low pass filter by using C1 and R1. So this basically forms a low pass filter. Now you might think why we are using the low pass filter. The reason why we are using this because our carrier frequency is usually higher than the information signal frequency. So if we use the low pass filter, then what will happen, it will pass the information signal because it is of a low frequency, and blocks the carrier signal because that is of a higher frequency. Now here, the rectified waveform from D1, it will be passed to capacitor C1, where the role of this capacitor is to charge up to the voltage of each positive peak of the rectified radio frequency signal. And then we have this resistor R1. It is also called a bleeder resistance. And if we don't have this R1 resistor here, then what will happen, C1 would just charge up and hold the highest possible DC level. So that's why we need to have the R1 so that it can discharge the voltage also. Here the time constant of R1 and C1 is designed to be very short as possible, so that the voltage on the C1 will follow the AM envelope as close as possible. These two signals you see is one is with CM, without CM C1, and another one is with C1. So you see here C1 is a part of it, this filter C1R1. So in this one, when there is no filter, then at this test point B, we will get a signal like this. And if we use the filter when C1 is present, then your waveform will look like this. And this bottom waveform basically consists of the information and the DC component, and the DC component is actually useful and it can be used to indicate the signal strength, and it can also be used to operate the automatic gain control circuit in a receiver, which we'll learn about that in later lectures. So now here the DC component which is present in the signal is actually not very useful for audio amplifications, for audio amplification. So it can be removed by using a capacitor over here, C2. So with the help of this C2 capacitor, the DC levels can be, the DC component can be removed. Now next is the TRF receiver. So the signal processing approach for a simple radio receiver is the first electronic approach that was used previously, and it is known as the tuned radio frequency, and this TRF you see is the short term for that, tuned radio frequency. And so here in this picture you see the modern version of the tuned radio frequency, and previously what you saw so far was the old version. And this TRF has fairly good performance, and it has, if you see, it has integrated circuit U1 and which mainly do most of the work, and it is this U1 is designed as a TRF radio receiver on a small chip, and it consists of three stages. The first one consists of 9 stages of radio frequency amplification with over 70 dB of available gain. Second consists of an active AM detector using a transistor as a diode, and third, it consists of an automatic gain control circuit to compensate for any signal fading. So this U1 basically needs 1.5 volt DC power supply, an RF input signal, and a detector filter capacitor. And the output of this U1 is a detected audio signal which needs only power amplification in order to drive the speaker. Now here, through this loop stick you see here, it is basically working as an antenna. Through here we get the input signal. So this loop stick is basically serving two purposes. It is acting as an antenna, but is also parallel resonated by a variable capacitor, which you see here, C1. And so they both are making a band pass filter and also a frequency selector circuit. The value for C1, you see it is a variable register. It is adjusted to select the station frequency, and the L1 and C1 produce the filtered output, which is the carrier frequency, and the signal value is very small in size, and that signal, that carrier signal from L1 and C1 basically enters to the U1 chip. So here U1 amplifies the RF signal and detects it, and U1 is also used to provide the DC power for the IC, and it extracts the information. Now the recovered information signal is basically passed through this volume control circuit. You can see through this R6, which is really just a variable voltage divider, and the upside of the circuit you see these diodes C1 and T2. These are forward biased by R3 and R3 and this R5 to provide the 1.5 volt operating supply for U1. And these components act as a simple voltage regulator. And here you see this C4 filter. This filters the DC power supply for U1. Now this LM386, it is a complete audio voltage and power amplifier on a one chip, and here you see this C5. It is used to set the gain of the LM386 to the maximum value. You see here C7. It AC couples the amplified audio signal into the speaker, and then you have C11 and C8. These are power supply filters which are very important in a receiver. Now there are basically two problems with this TRF receiver. So first is the selectivity of the TRF receivers. It is not constant, and second is that it is nearly impossible to design a TRF receiver for high frequency operation. So these are the two problems with this TRF receiver. Now moving on to the next slide. So here in this slide, it says to calculate the bandwidth for the modeled tuning circuit below at the following frequencies, which is for 540 kilohertz bottom of the AM dial, 980 kilohertz middle of dial, and 1620 kilohertz top of the dial. So here you see the circuit, and this is your antenna and the tuning capacitor, and then the load is connected, and it says the RL load is the combined coil loss L1 and the input resistance of U1, which we saw in the previous circuit. It represents all the losses in the tuned circuits. Now here to calculate the bandwidth, we must need to calculate the quality factor Q, and which is given by this formula RP by XP. And to calculate the bandwidth, we will use this formula frequency by Q, where Q is the quality factor. And here you see selectivity. It can be defined as the ability of a receiver to select or choose a desired signal while rejecting all others. So now let's see what will be our value for the bandwidth for these three different frequency. So when you're using at 440 kilohertz frequency, then you will get the bandwidth of 9.152 kilohertz, and So you see that this is a reasonable bandwidth, and since an AM broadcast uses 8 kilohertz of bandwidth, by repeating the procedure at 980 kilohertz, we will get the bandwidth of 30.2 kilohertz. And then further, if we use the frequency of 1620 kilohertz, then our bandwidth will be 82.2 kilohertz. So here an ideal receiver should have a constant bandwidth and therefore the constant sensitivity, but here we don't see that the bandwidth is constant. And you can read here the receiver's bandwidth has increased from 9 kilohertz to more than 80 kilohertz over its tuning range, and this is actually unacceptable performance. More than 8 stations might be recovered at the same time. Why? Because stations are spaced every 10 kilohertz on the AM broadcast band. So if you calculate, it will come around 8 stations. So we see that the bandwidth is not constant here, and so this TRF approach fails miserably here. So we see bandwidth of any tuned circuit depends on the frequency it is tuned to, and generally for a parallel loaded capacitively tuned circuit, higher the tuning frequency is, the greater the bandwidth, and in that case the selectivity becomes poorer. So for any tuned circuit to have a constant selectivity, the tuned frequency of the circuit must not be changed. And here we have another problem, which is operation at frequencies above a few megahertz, and that is also a problem. And in that case it becomes impossible to find the discrete inductor and capacitor components that will satisfy the tank requirements. Now moving on to the next slide. In this slide we'll learn about super heterodyne receiver. And super heterodyne receiver, it is a different kind of receiver in which the incoming radio frequency signal is first converted into a constant frequency signal, which is also called as intermediate frequency signal. So it's the same thing, and actually prior to super heterodyne receivers invention, the engineers used to spend great amount of time and efforts getting reasonable performance from the tuning circuit in a receiver. And the receivers in this super heterodyne technology type, it should satisfy 3 important factors. First is the selectivity, which means tuning or the selecting the signal of particular frequency. Second is the sensitivity, so every weak signals should be captured nicely. And third is the fidelity, so the fidelity should be high. So basic message signal should not be distorted, must be closed replica of the information message signal. So here it says once the signal has been converted to the intermediate frequency, it is band limited, amplified, and detected. So the problem of the bandwidth being not constant has been resolved here with the use of super heterodyne receivers. So we are going to see next why is an IF frequency is used. So converting the incoming carrier signal to an IF frequency has 2 important advantages. So as I told you, first is the bandwidth of the receiver becomes constant because the tuned circuit operates at a constant frequency. Second is we are able to work at a higher frequency or a very higher frequency, and beyond becomes possible. So now here we see the block diagram of a super heterodyne receiver. So you see a receiver, and so data is basically a signal is basically obtained from this antenna, and then it is sent to this frequency converter section. So you see that this is new here in super heterodyne receiver frequency converter section, and this section basically helps in getting the constant bandwidth, and it will also help in making the receiver to be able to work for higher frequency or very higher frequency. So after this frequency converter section, we are able to get the constant frequency signal, which is further sent to the amplifier and then to the demodulator. And you know that in the demodulator or at the detector side, the carrier frequency is and thus information signals are separated, and at the output you get the information signal which is amplified and sent to the speaker. So it says in a super heterodyne receiver, the information carrier signal frequency is changed to FIF by the frequency converter. The IF section then amplifies the converted RF signal. Since the IF has a constant frequency, its bandwidth is also constant. Now in the next slide we are going to see this frequency converter section and what are the modules inside this section which is helping in making the bandwidth constant. So here you see there are three important components in the frequency converter section, which is the pre-selector and the mixer, and third one is the local oscillator. So the purpose of this frequency converter is to produce a constant output frequency, which is known as FIF, regardless of what input carrier signal is being sent. So let's first learn about the mixer and what will happen at this stage. So this mixer basically consists of a non-linear device, usually made up of a diode or transistor, and this mixer causes non-linear distortion of the two signals which are coming from here. So you see here FC is the carrier frequency signal is coming through this pre-selector, and the FLO, which is the local oscillator frequency signal, is coming from here. So these two signals basically enter into the mixture, and it causes a non-linear distortion of the two signals being applied to this mixture. And when signals are distorted in the receiver, then new frequencies are basically created here at the output side. So if these two, let's say if two frequencies are applied here, then at the output we will have basically four different frequencies. The first frequency will be the original frequency, which is FC. Other will be FLO, which you will be sending, and the next two will be the sum of two and the difference of two. So here we see at the output we get four different frequencies: first FC, second FLO, third FC plus FLO, fourth FC minus FLO, or FLO minus FC. So all these four frequencies we get at the output. And here the pre-selector you see is always tuned to the carrier frequency, and this pre-selector is not a narrow filter. It may even allow adjacent carrier frequencies to pass into the mixture. Now here the pre-selector and the local oscillator circuits, they are mechanically interconnected, you see through this dotted line, so that they will track each other. And when these two circuits properly track, then they maintain the proper FIF frequency signal, which is obtained from here. So let's read here what it says. The frequency converter is responsible for converting the incoming carrier to the IF frequency. It consists of a mixture and a local oscillator. Now moving on to the next slide. So as I said before, that mixture, in the mixture, if you send the signal, carrier signal, and through the oscillator, then you will get 4 different frequency, and that's what it is written here. You will get the original frequencies, which is F1 and F2, and if we see in our case, F1 is 100 kilohertz and F2 is 500 kilohertz. And then we have another frequency which will be the sum of these two frequencies, and the sum of F1 and F2 is going to be 600, and 600 is going to be our new frequency, and the difference of these two frequency is going to be our another frequency, and here the difference is 400 kilohertz. So it's the same thing, 100 500 kilohertz, and then 600 kilohertz and 400 kilohertz. Now it says in a frequency converter, the local oscillator is tuned to the proper frequency in order to convert the incoming carrier to the IF frequency. There are two LO frequencies possible. First is FC minus FIF, and another one is the FLO is equals to FC plus FIF. This one is called your low side injection, and this is called your high side injection. High side injection is used in broadcast receivers and will be used in the examples we will see here. So you may hear the terms like high side injection and low side injection. So those are the terms basically used in practice, and these are just a like fancy words of saying that the local oscillator operates either above or below the carrier frequency. So now in this example, you see you see a frequency converter, and then you have a pre-selector, mixture, and a local oscillator. From here we are sending 10 kilohertz frequency carrier frequency signal to the mixture, and we know that at the output we will have 4 different frequencies based on the local oscillator frequency we are sending through this. We are trying to maintain the 455 kilohertz kilohertz of a difference, and so we need to get our frequency of 455 kilohertz out of the mixture, and because that is the IF frequency IF frequency signal we want at the outputs. So if we know that what we want at this output of the mixture, then we can select the frequency of the oscillator over here. So if it is so it will be 1165, and based on that we will get all these 4 different values of the frequencies. So here it says the converter above is tuned to receive 710 kilohertz using high side injection. The mixture output goes to the IF where only 455 kilohertz component can pass. Now this is another example. To calculate the frequency of each, you have to calculate the frequency of each tuned circuit and all mixers outputs. Which mixer output frequency can pass through the IF amplifier? So here the difference we want for 455 kilohertz, and this difference is mostly used by AM broadcast receivers, so we are going to use the same value here. Now here incoming signal is 810 kilohertz, so we can make a guess by this value, because we want FIF here 455. So if you do the math, then you will get the value for this local oscillator. Now comes the tracking, and this slide says in order for the mixture to produce the IF frequency at its output, the difference between the incoming RF carrier frequency and the local oscillator must be equal. So you need to make track between the local oscillator and the carrier frequency signal which is coming to the mixture. then only you are able to produce the or able to have the FIF. Tracking is the ability of the preselector and the local oscillator to maintain a constant difference of FIF as the receiver is tuned across the band. So it's a same thing. A superheterodyne receiver achieves tracking by either mechanically or electronically ganging the preselector and local oscillator circuit, so that when the tuning control is adjusted, the two oscillator change in unison. Now, if the mixture and the local oscillator work together to convert the incoming carrier frequency into the IF frequency, then why do we need the preselector circuit? Why can't we have a direct incoming signal going into the mixture, and then only and then we have just only the local oscillator circuit to create the local oscillator signal? So we are going to learn here why do we need the preselector circuit. So let's say you are sending a signal of 710 kilohertz, which is your carrier frequency, and FLO, which is the signal which is going from the oscillator, local oscillator. From there you are sending this frequency, and you are trying to make a difference of 455 kilohertz, which is your FIF. Now what will happen if you don't use the preselector circuit? Then a image frequency will be created. You see here 1620, and which is also forming a 455 kilohertz difference with the local oscillator frequency. And this image frequency is basically sometimes selected by the mixture, and then based on that your signal is being sent, and which is not desirable actually. Our desirable frequency is this one. So let's see what it says. The image frequency is the second frequency that will beat the energy from the local oscillator to produce the IF frequency. The image frequency appears on the side of the local oscillator frequency opposite the carrier frequency, which is this one. For any LO frequency, there are always two frequencies that can mix with it and produce FIF. Now, with the help of preselector circuit, what we do, we select the frequency which we desire, and then that frequency is being sent to the mixture, and that is the reason why we use it. Let's see what it says here. If energy is applied to the mixture at the image frequency, it will be converted to the IF frequency by the mixture. This is highly desirable. The function of the preselector is reduce or eliminate the image frequency energy before it can get into the mixture. So it means we need a filter. A preselector performs this action of selecting the particular frequency, and preselector is tuned to the carrier frequency. It will reduce or eliminate the image frequency. Now we are going to see the summary. And it says a superheterodyne receiver operates using the principle of frequency conversion. The receiver moves the desired input carrier frequency to the intermediate frequency, or the constant frequency, we can say. Conversion is achieved in the frequency converter section, which consists of a preselector filter, local oscillator, and a mixture. All superheterodyne receivers can respond to energy at the image frequency. The preselector is responsible for eliminating this energy prior to mixing. So this is the end of the lecture. Thank you so much for watching.